Okay, recording started. Sorry. Thank you. So what I was saying that if this cache is shared, then even after distributing it among multiple ties, then also the bank is shared, the cache is shared. So if there is a request here in the local L1, if there is a miss in L1, then it means we have to fetch the block from L2. So but here it doesn't mean then every time you'll go to this bank first. Before going to L2, it will first check that which bank the block is mapping, same based on some bank index. So based on some bank index, like the set index concept of set associative cache, if the based on bank index, the block is mapping to this bank, then once there is a miss in L1, it will go from here to here, this bank, and you have to fetch the data from that particular bank. So these concepts you have to understand, and based on this you will see this kind of design TCMP. Though I am not using TCMP much in this course, but it will require if you want to work as here for your, maybe it will require for your term paper, or in future if you want to work in this area more, then this type of design TCMP will be required. Also the partitioning, one recorded lecture that I'll upload for cache partitioning, in that lecture I will use this design TCMP. So here you have to understand this. Suppose one tile, I am zooming one tile here, T4 is zoomed here. So each tile has a core, an L1 cache, and a L2 bank. So this L2 bank and the L2 bank that I have shown in left side are same. So if there is a the core is requesting for a block, then we'll first search in its local L1, and if there is a miss in local L1, then we'll find out the bank index of this block. If the bank index of this block is 15, then we'll, if there is a miss in L1, then from this L1 means this is actually the zoomed version of this, right? So this is actually tile. So from this tile we have to travel through NOC, you have to go to this 15, and from this 15 we have to take the block back here. That you have to understand. There will be no connection with local L2 bank here, because it's, so what, why I'm explaining all this thing, because here your bank, the LLC shared but distributed. It's not like private and distributed. Okay, so let us start with utilization issue. When we'll discuss utilization issues in LLC, mainly I'm saying LLC in TCMP. So this diagram is TCMP, right? Tile based CMP, tile based chip quality processor. So each L2 bank here, if you concentrate on each L2 bank, each L2 bank is a set associative cache, independent set associative cache. There are 16 tiles, so there are 16 LLC banks. Okay, so utilization issues means you have, suppose you have a 16 MB of LLC, but somehow you are not able to use all the 16 MB. Every time when you are executing the computer, maybe only 10 MBs or only 12 MBs are using, other 4 MB you are not able to use. Why? Because of mapping issues and all. Because if you have a fully associative cache, then you can fully utilize the cache, right? But if you have a fully utilized associative cache, then there are all associative and there is only one set, right? So any block can be placed a map in any position, so you can fully utilize it. But instead of this, if you have a set associative cache, right, like this, so what is happening here, once you go with set associative cache, then mapping issue of mapping is coming, right? So maybe some blocks are mapping here in this set, and and it may be possible that there is one set here which this is the last set. Suppose in last set a very less number of blocks are placing. Why? Because according to mapping, some fixed block will always fit in this set, and when you are executing application, in that application based on some mapping, only less number of blocks are coming here. So in that case, what is happening, you are not able to utilize the cache completely. So that is called utilization issue. That utilization issue will not be the case if you have only a single fully associative cache. Okay, so utilization issues can be divided into two parts. One is called local utilization issue. Local utilization issue means local to each bank here. So you have to understand each bank is a set associative cache. So local utilization issue means the problem faced by each set associative cache. So what is that problem? The problem, as I have explained here, then it has been observed that there are some set in the set associative cache which are heavily used, which are facing heavy conflict misses. But at the same time, it may be possible that there are some set exist where the load is very less and the number of misses is very less. To explain this, you can check this diagram here. In this diagram, this y-axis, maybe the diagram is looking small, but this side it is set number of a bank. So you can see the in this bank there are 512 sets are there, and this side these are number of misses, number of conflict misses. So you can see there are some sets here where the number of misses is very high. It means that these sets are heavily used set. Also you can see there are some sets here which are number of misses are very low. So these sets are lightly used set. So it means that even if you have a set associative cache, out of this set associative cache, this set is facing heavy misses because lot of blocks are mapping to this set, and this set is almost ideal. So it means that you, because of an inefficient mapping, or you can say because of this fixed mapping of set associative cache, you are not able to utilize the cache space completely. And if you don't utilize the cache space completely, it means that there will be misses, and if there is a misses, then you'll go to main memory. If you go to main memory, it will consume more time. If it will consume more time, then ultimately your average memory access time, that we call m8, will increase, right? And if your m8 will increase, then ultimately it will affect your cpi, ipc, or you can say the performance of the computer. Okay, so this how so this is one issue that is called local utilization issue, and another issue is called global utilization issue. In global utilization issue, to understand global utilization issue, you should remember the concept of SNUCA also, TCMP and SNUCA both. So today also I have explained that if there is a miss in L1, then we will first search the bank index, and based on those bank index, we will go to a particular bank. That is actually called SNUCA design, right? I think I have explained and I have already shared slides on SNUCA. So this design is called SNUCA design, static NUCA design. And the dynamic nuka is not required here, so I will not explain. So since your bank index is fixed, so every time whenever you want to go to last level cache, you will go with bank index, right? So since again there is a indexing policies there, it may be possible that there are some banks which are heavily loaded, and there will be some banks which are lightly loaded. So this is called global utilization issue, and the graph that I'm showing in right side is an example of global utilization issue. You can see this side it is number of banks. So this is same, the experiment that is taken, that is performed for this graph is on the TCMP that I'm showing here. Actually both the experiment that I'm showing here by experiments are done by me. So I know the setup. So in this setup only both the experiment performed. So left side graph I'm showing for each bank, because each bank is a associative cache. The right side graph that I'm showing here, I am taking, I am calculating that load or number of bank accesses on each bank. So there are 15 banks, and in y-axis I'm showing the total number of bank access, and there are three lines here, right? So there are three benchmarks. These are the benchmarks. There are three benchmarks here. So you can see that there are some sets here. See this, there are some banks. These banks are heavily access banks, so there are load of these banks are more. But you can also see there are some banks here, there are almost ideal banks are also there. So it means that when there are multiple banks executing, there are some banks which are heavily loaded, and some banks are not. So assume that this bank is heavily loaded and this bank is almost ideal. So again you are not utilizing the cache space properly. So this is the problem statement. Till now I have not explained any solution here. So I've just explained the problem statement. So problem statement is utilization issues. There are two part, local and global. So let us go to next slide. So you can see I have so this is effective LLC utilization, means how you can utilize your last level cache of TCMP effectively. So this was also the topic of my PhD thesis. So you can see there are two problems. First problem is local optimization issue and global optimization issue. So here what we will do, we'll discuss both the techniques here. So if we go with local optimization issue, then from local optimization side we'll discuss four paper here. These papers are called VUE, SBC, GCAS and FSDEM. And from global optimization side we'll discuss two papers, TD NUCA and TLD NUCA. Here all these paper that I'll discuss, these are actually a solution how to handle optimization issue. Left side papers are the solution for handling local optimization issue, and right side papers are the solution for handling global optimization issues. So let us see the papers here. I think papers are displayed here. So you can see in the left right side, the both the papers are my papers. So but let me add a disclaimer also here. So you no need to study this part. Why no need to study? Because I cannot give all the load to you because midsem is very near, right? So I can only give you restricted loads. So I'll explain these papers 4 and 5, but it is not required to understand why not important for your exam. Also from right side, since the exam is very near, though I'll explain all the four papers, 1 2 3 and 4, but the SVC you only need to understand the concept of SVC, but in exam I'll not ask any questions. So basically in this week you need to from this section utilization you need to study 1 3 and 4 properly. Okay, so let us start with paper number one, that is VUA. So I'm explaining this VUA with a single slide only because the concept is very easy and it's proposed in 2005. Though it proposed in 2005, but it is proposed in ISCA, I think. So it's a very good place, and paper is also very interesting. And you can remember this author also, Qureshi. Even we start with 2005. I think the UCP paper was also from Qureshi. Today I'm explaining on paper. I think the DIP paper was also from this author, same author, I think. So many papers from the same author I'm explaining in this class. Even when after midsem when we'll start discussing the recent paper of 2022 or 2020, then also we'll read the papers of this author. Okay, so let us start with a very easy technique VUA to handle local utilization issue. So this is your site associative catch, suppose. And in last lecture, I think I'm not sure in your class or in BTech, because I'm taking architecture for both BTech and you, so I'm not sure in which lectures I've explained it. So what I said that uh, 1 2 3 4, right? So normally when we say set associative cache, we only design this type of diagram, right? A 2D matrix kind of diagram. But in physical design, this diagram is divided into two part. Actually, this you can say as data part, and this is the tag part. It is divided into two part, tag and data part. So in tag part, what we store here, we store tag portion and all the metadata. Metadata means the shared information that we discuss, which is required for the coherence part. Shared information, then data bit, all other informations are stored in this part. This is called tag part. So tag array and data array, there are two parts for every set associative cache. Okay, and these are that is a one-to-one mapping, means you no need to store any pointers, because this has one-to-one mapping with this location, and same in this has one-to-one mapping with this location, right? So this type of design is important because when we want to search a data in the search a block in the cache, suppose the cache is of 4 MB, so it's a huge space. So instead of this, if we go with tag, then it will be only a few KVs. So better to search in this tag array, so it will save time also. So first search in the tag array and find if there is a hit or miss. If there is a hit, then we'll know the corresponding data position. We'll go to the corresponding data position and fetch the data from the corresponding position. And if there is a miss in tag, then obviously data is not in the cache, right? So that's why tag and data normally separates. But the main point you have to understand here is one-to-one mapping. You can see there is a one-to-one mapping. If this is also four-way associative, then the tag part is also four-way associative, and there is a one-to-one mapping between the entries here. Okay, so now what VUA is saying. So this is the actual set associative cache, right? And on here, this set associative cache face the issue of local utilization issue that I've already explained. So how VUA is solving this problem? So VUA is saying that okay, what we will do, we will not maintain the direct one-to-one communication between data path and tag, data and tag. Means here there is a direct communication, right? This has a direct mapping with this. So they said no, will not follow the direct mapping. So and what they are saying that instead of four-way associative tag, we'll use eight-way associative tag. So you can see this is four-way, data is still four-way, this is four-way. You can say this is four-way, but this is eight-way. So obviously there is no one-to-one mapping, right? Because the number of entries here will be more, double. 1 0, 1, 2, 3, 4, 5. So there are six. So there are 24 entries here, right? 24 entries here. 24 blocks you can place in data path, but here it will be 48. 48 entries. Why 48 entries? Because in each set the associativity is, instead of 4, there are 8-way associative cache. So now why they did this, why instead of 4, if I actually, it should be here, right? It should actually only the left side is valid, the right side is extra here. So by this extra entries we are saying that if some set is heavily loading, means if some set need more space. Heavily loading means what? How can you handle it? If there is a set which is heavily loaded, means it facing more misses. How can you handle it? Only way to handle it is increase the associativity or give this set more space. How can you give a set more space? It is not possible in physical design, right? So that's why they are saying that if we increase the associativity of a tag part from a 4 to 8, then a set can store at max 8 ways. So in that case, that instead of 4 at max, if it is required, then it can store up to 8 ways in a set. Okay. So now the problem here is all the set here, all the set cannot use 8 ways, right? If all the sets started using 8 ways, then total entries required, total data required, data entries required is 48. But if you see the right side, total data entries is only 24. That's why they why they design why they go for this type of design. They assume that only few set are heavily used, right? And those heavily used set, and at the same time, as I said, there are some set which are lightly used. If there is not this difference, means some sets are heavily used. If you remember my graph, there are some sets here heavily used and there are some sets here lightly used. So the extra ways, that is, or extra blocks that is required for the heavily ways, those will be provided by the lightly ways. That's why it will be balanced. So this is their idea, that so instead of 4 ways, they will go with 8 ways, and such that the heavily ways set can use more ways. But now how they will maintain the mapping? Because suppose these locations, there are 8 locations here, and there in this set there are only 4 locations, so you cannot go with static mapping. So that's why they maintain some pointers. So that pointers are called forward pointers and backward pointers. So every location here, with this they also store a pointer here. This pointer is saying that which data entry position it is currently pointing. So that pointer will be stored here. In same way, in data portion also there will be stored a pointer. It's called backward pointer, which will point backward to the tag part. So forward pointer and backward pointers are required here to maintain the mapping. Otherwise, it's not possible to handle. Okay. So I think this till this part is clear. This is easy also. And in tag part, they will maintain replacement policy, LRU replacement policy, suppose. But the challenging part is replacement policy for data storage, because you can see in data part now we are not maintaining any associativity. Any block can be placed in any location, right? Because we are maintaining the associativity here, and it may be possible that this location is now associated with this location. It may be possible because in data part we are not maintaining any associativity. Whenever a block we want to place, we first check in the tag part, and if in tag part if there is a free space, we will place it there. And based on this, suppose this data part is now full, so there should be some replacement policy in data part also, which will replace a particular block, and in place of that block we can place a new block. So the question here is, since there is a no concept of set in right side, then the replacement policy must be global. So let me explain you one concept here. Assume that your data part is full. Data part is full, and maybe some blocks are here. I'm not using all blocks, maybe like this. So based on this tag, your current data part is the current data location is full. Now a new request is coming, and first we search in tag parts. Assume that it is a mapping in the first set of tag, and the block is not here, so it's a miss. So you can see there is one place is still available in tag part. So I can place the new tag part of new block here, but the question is where I will place the data part, right? Because data is full. So in that case we have to replace one data, but which data? Now the question is which data, right? One option is just you need to you try to find out a block, LRU block from this point, and the corresponding block you can data you can remove. Instead of this, what they did in this paper, they use a global replacement policy, but a efficient global replacement policy. So based on that global replacement policy, they will replace a data. So suppose based on that global replacement policy, they are choosing this data as victim. So if they choose this data as victim, then what they will do, they will remove this data. If they remove this data, the corresponding entry of this data also need to be removed. So in that case, we will go with the backward pointer. There is a backward pointer stored here. Suppose that backward pointer is pointing to this location. So this data and this tag will both will be removed. This is the first point. After removing, then this position become empty. So in that position, the new data of the new block will be stored here. Okay, so here the forward pointer will just also change, and after pointing it here, the backward pointer will also change, and now it will point this. So I hope you are understanding the concept of forward pointer, backward pointer here, and also the global replacement policy that they use for data part. And for tag part, it is same. They will use LRU replacement policy. So now the question is, why they only replicate, or why they only double the size of tag part? Why not data part? So that's why the data path is very huge, right? The main content of cache is stored in data path, right? In tag part, only metadata are stored. So it is still possible, though there is a hardware overhead is still there, but at that time, at 2005, it was still possible that we can go with a with the double size of tag, but it is not possible that every time you just increase the cache size or increase the associativity or cache size, right? So suppose you are designing a chip, and for based on this you have placed you have decided to go with the 4 MB of cache, and now someone is saying no, instead of 4 MB go with the 8 MB of cache. Then that is not possible, right? The cost is also a matter, the cheap area is also a problem. But instead of this, if we go with this design, maybe previously it was suppose 128 kV, and now if we go with double size tag, then maybe it will increase to only 256 kV. So it is still possible, right? Though there is a hardware overhead, but it's still possible. So that's why they went with this design. But obviously this design has disadvantages because it is proposed in 2005 and we are discussing it in 2022. So now we will understand the disadvantage. First disadvantage is now doubling the tag array. It means 50% hardware overhead, I mean 100% hardware overhead on tag side, right? So that is a hardware overhead for today. And also as I said, they need to maintain forward and backward pointer on both sides. So these forward and backward pointers also waste some storage, significant storage, not some it's all this overhead is also significant. So these are some disadvantages of VUAs. So the next concept that I will discuss in that concept, the forward and backward pointers are not required. That is called SBC. So I'll quickly explain SBC. Why? Because I already mentioned that SBC is not required for your course, but you read it once because it's very interesting. I'll not show you the paper, but I'll upload the paper in Google Classroom. And if you are interested, you can read this paper, and you read the paper slowly. Each and every line is interesting, and you will understand the paper. Once you understand the paper, you will enjoy it, because this is a very good the way of writing is also very good, and it's a very interesting paper, SBC. So what SBC says, that no, they will not maintain separate means double size tag array, and also they will not separate the one-to-one mappings also. So what, instead of this, they will maintain several counters here, set wise counters, and based on this counter, they will trace dynamically. When the program is executing or computer is running, they'll dynamically trace that which are the set which are heavily loaded, which are the set which are lightly loaded, and they will associate two set dynamically. Suppose dynamically they found that the first set is heavily loaded and the last set is almost ideal, then dynamically they will associate first set and last set. It means that first set can now store its data in set first set as well as in last set also. So this type of association they can done dynamically. Also what they did, that they will constantly monitor it, and after some time, if they found that no, the set one is not now at this moment it is not very heavily loaded, then they will change the associativity. Means association will be dropped. It may be also possible that after some time the last set which was previously lightly used, this last set now becoming a heavily used set. So in that case this association should not be there, right? Because according to this association, first set is heavily used and last set is lightly used, but after some time is last set becoming also a heavily used set, then we should change the association. So all this association means joining two set and then changing the association and all these are explained in this paper properly, so you can read this paper. So now one important point is if there are two set now currently associated, then how the searching is performed. So for example, if there is a block currently mapping on set 1, so if we can now, and the set 1 is now currently associated with the last set also, then if you have to search both the set, and then only you can say whether the block is a hit or miss, right? So in this paper they said sequential search. Sequential search means first we will search set 1, and if we find the block in set 1, that is fine, otherwise we will search the last set also. And after searching both the set, if the block is not in the cache, then it's a miss, then we'll go to main memory to fetch the block. So this is a sequential search here in SBC. So and this is the main problem of SBC also. In SBC, if suppose your association is only two sets, suppose the set 1 is more heavily loaded and we have assigned two sets, means last two set are assigned to this first heavily used set. So in that case, you have to sequentially search all the three set to find out if the block is hit or a miss. So this sequential search is a problem of SBC. Another problem of SBC is it maintains many counters, and maintaining all these counters is also a hardware overhead. Okay, so I'm stopping this discussion here for SBC because I don't want to discuss more, because as I said, this paper is not important for your midsem also yet. But I think one more point I need to discuss here. There are two types of overhead here. See, I say there are counters. If you can see, I have designed some boxes here in right side as well as left side. By these boxes I'm considering counters, that there will be set wise counters based on which it will check that whether a particular set is heavily used or not. So I say that when we use this counter has storage overhead, right? Because we need more storage, we need more hardware circuit to design those counter. This is one part. And the another problem I said here, sequential search, right? One by one it will search. So there are two type of overhead. So the first overhead that I said, sequential search, it has direct impact on your performance, because this falls in critical path. Critical path means if you request for a particular block, and you can only decide whether it's a hit or miss after searching all the sets here, right? So searching all the set needs some time. So that time is falls in your critical path. So you have to understand this type of words or this type of lines you will see when you read papers, critical path. So this time is falls in your critical path. But the two module that I have designed in left side and right side, so what you will do here, this module will increment and decrement some values, right? And based on these values, periodically they will check that which set is heavily used and which set is not. So these things are actually performed in background. When these things are analyzing, at that time cache can perform its work, cache can do its work, right? This cache memory can do its work when this module will analyze that which blocks are heavily used and not. So though this right side and left side, these hardware module are increasing the hardware overhead as well as increasing the storage overhead, but they are not, the latency that they are consuming, that it's not falls in the critical path. Okay, so many times when we write a paper, we write like this also, that though there are some overheads, but the module that I have added, those module are not added any latency in the critical path. But you can see this search that we are performing in SBC, that latency is adding in your critical path. If this point is not clear, then you can ask me later also. Why? Because this point is important. So next class, I'll explain CMP, SBR, and FSDM. These two are the techniques proposed by me, and these two are related with BUA and SBC. But I'm stopping this SBR and FSDM because let us go with year wise. So I first explained BUA 2005, I think. Then SBC, I think it's proposed in 2010 or I think 2009. Then I'll go with another paper. It's called Zcash today. Zcash is proposed also in the same time, 2010 or 2009. Then tomorrow I'll explain SBC and FSDM, which SBC I have, CMP SBR, I think CMP SBR I have proposed in 2013, and I think ZCAB means FSDM I have proposed at 2017. So I'll discuss these two paper tomorrow. Today I'll quickly explain one more technique that is called Zcache. So before explaining Zcache, I'll explain you one concept called skew associative cache. Skew associative cache is different than SAT associative cache. SAT associative cache, every property you know that if you want to map a block, first you will fix the set, and based on this set, means this block will be always placed in this set. So there are four position here, right? W1, W2, W3, W4. Any of this position, the block can be placed, but within that set. That is called SAT associative cache. But in so there is only one hash function, right? Based on every block, there will be a hash function here. Based on this hash function, suppose the block is y, so first we'll go to this set and we'll place it any of these four positions. This is called set associative cache. In skew associative cache, you will have four hash functions: h1, h2, h3, and h4 for each ways. So now if we apply hash 1 for y, then maybe it is mapping here, suppose. If you apply h2, then for way 2, then maybe it will map here, and for h3 maybe here, and h4 maybe here. So it means that a block y is not going for a particular set every time. So it is, there are four hash function, and if you want to place it in first column, that is way 1, this is your way 1, right? So if you want to place it in first column, then you will apply the hash function of h1, and based on this there will be a location fixed. If you want to place it in the second way, then you will apply the hash function of h2, and based on this hash function there will be a fixed location here. And for third way, there is a third hash function, so based on this it will place here. So you can see that in each set the block has different way position, right? So here this is the position in the for way number 2, this is the position like this. So you have to understand this is the concept of skew associative cache, and this concept is parallel to set associative cache. There are advantages and disadvantages of both skew associative and set associative, but I'm not going to more detail about that. But at this point, you just remember what is called skew associative, and let me go to a paper. This is called Zcache. So Zcache is a very interesting concept, and this Zcache is proposed in 2010, and it is also a technique to handle the local utilization issue. But the underlying cache that they assume is skew associative cache, not SAT associative cache. So I'm not explaining all the papers here line by line, but I'm advising you to read the papers read the paper once. You will understand the concept written. Whatever things written in this paper, it is already discussed in this class, and I don't think there will be any new concept you will find here that it's not possible for you to understand. So that's why I'm removing ignoring all this and directly going to a example from where I'll explain you the complete idea here. Okay, yeah. So from here, I think the first diagram, they are also explaining here the skew associative cache. The first diagram here up to this point here, they are also explaining the skew associative cache. So here, if we apply y, they are using three ways. So y is mapping here in way 0, it is mapping to 5, that is A. And in way 1, it is mapping to D, I think. It is mapping here in D. And in way 2, it is mapping in place of M. So suppose this is the current situation of the cache, and at this moment if you want to place y in this cache, right? So obviously cache has no space, but which are the position or which are the place where you can which are the location where you can place y? So that will be given by this three hash function. H3 means in way 0 you can place y in place of A, in way 1 you can place y in place of D, and in way 2 you can place y in place of M. So that is showing here y, and you see the first layer here. First, this is the first level, right? This is the level 1. So in this level you can see y can be placed either replacing A or replacing D or replacing M in skew associative cache. That part is fine. That is called skew associative cache. Now in Zcache, what they do, they use the concept of skew associative cache, but they check multiple levels. So now let us consider that to place y, I want to replace a. Okay, so now so if I want to suppose if I go skew associative cache, and these are the three candidates, right? Based on these three candidates, I have to remove one. So assume that a is the LRU of these three. So simply remove a and place y in place of a. That is fine. But what Zcache is saying, no, just check the mapping of a. Where are the location where a mapped? A will also go with h0, right? Then h1 and h2. So if we map with h0, obviously it will map to this position, which is I think 5, which is 5, right? Locations are written here, right? 0, 1, 2, 3. That's why obviously a if I map a with h0, then outcome will be 5. But if I try to map a with h1, then outcome will be different. Outcome is suppose 2, and here for h2 outcome is 1. Outcome will be different. For y, what was the outcome? For y, outcome for h0 was 5. That's why it is conflicting with a. For h1, outcome was 4, and for h2 outcome was 0, right? It is showing here, right? A, this is actually 5, then here it is 4, and it is 0. So and if we go with a, then a, for a it is coming with 5, 2, and 1. So which are the blocks with whom a is conflicting? A is conflicting, first of all, a is here a is conflicting with 2 and 1 also. So from a, two more blocks are coming, k and x. So k, with k and x, both are coming. In the same way, if we apply k, then there will be two more dependencies are here, L, M, and for x there will be two dependencies, N and E. So in this way, if I concentrate on this level, and there are a lot of candidates, right? There are a lot of candidates. Instead of first level, there are only 3 candidates, A, D, and M. If we go to third level, then there are many candidates. So now out of all these candidates, remember our main goal is to placing Y. We want to place y in the cache, but there is no space for y. That's why we are doing all this thing. And when we want to try place y, we found that okay, in first level a is the best candidate, a is the LRU candidate. But no, what we want to do, we want to check more. We are checking now that which are the location where a is dependent. So you can see that a is dependent on x and k also. Like if you want to place a, though I placed a in this position, means way 05, but there are two more positions where a can be placed, right? So those in those positions currently k and x are stored. The same way now again I check for k, and again I check for x. So in this way, from this is level 1, then level 2, and this is level 3. You can continue like this also for other means level 4 also, but let us fix it level 3 here. So now in level 3, out of all the candidates, find the LRU candidate. So assume that this is the LRU candidate, and here this is the LRU candidate. So let us remove n, and in place of n store y. Okay, so now if you replace n, and in place of n you want to place y, you cannot directly place, because the mapping policy of y is not allowing it. Mapping policy of y is not allowing it. Mapping policy of y is saying either you can place it in this position of way 0, in this position of way 1, and this position of way 2. So n, the current position of n is here. Let's see. Let me go into the red, I think so, otherwise it will be. So this is the current position of n, so which is not the position where y is directly mapping, right? Y is mapping the position which is below of n. You can see the mapping. So now if you replace n, how can you handle? So what they are saying, we'll replace n, okay, fine, and in place of n we'll place something else. Which block you can place in place of n? See in this dependency, this block x you can place in position of n, right? So what they will do, the n will be removed. They will move x from here to here. Okay, now the position of x is free. Now the in position of x, what you can do, in position of x you can place a, isn't it? Because a can place here, so you'll move a here, and now the original position of a is empty. So it means that this position is now empty. So in this position you can place y. So this is their replacement policy of Zcash. They are going with recursive replacement, you can say. Means it's not just a one step replacement, it's a multi-step replacement. Don't go, because there is an obvious question here that, sir, it is complex. Yes, it is complex, but with this complicated case, they are improving the performance. And then the next important question is how it is handling the local utilization issue. So if you see the first level here, if you go with this level, then you are only choosing the LRU block among the three, but here you are choosing LRU block among many blocks, right? So in this way they are increasing the associativity also. If there is a block which is, or if there is a set or which is heavily accessed, then it means that we can give more space, right? So you are checking more blocks and trying to find out the least recently used block, isn't it? So as I said that if you have a fully associative cache, then there will be no utilization issue. And instead of this, if you have a cache where there are four ways, then there will be utilization issues. But there is the intermediate thing also, right? Instead of four ways, if you have only two ways, my two sets, sorry, if that here there is only one set, this is fully associative cache, I think I said there is no local utilization issue. And this is the another extreme case. Here there are four sets, right? And each set suppose has four ways, so there are utilization issues. Instead of this, if you go for only two set and eight ways, then there will be less utilization issues, right? So this point you can understand here. In Zcash, they're trying to reduce the utilization issue by increasing this means taking a larger group to find out the LRU block. So now the question since it is a complex replacement policy, is it hampering the critical path here? So yes, there is a critical path issue also here. What is the critical path? See, calculating all this dependency and all, this doesn't fall in critical path. So one point here is you cannot directly say that this replacement policy, the time required for this replacement policy falls in critical path. Why? Let me explain. Because what is happening, suppose I'm removing everything. Suppose this is the core, right? And this is the core, and core is requesting for Y here. And obviously first time if you are going for Y here, and if you are doing all this replacement policy means you are mostly, this diagram is saying all these things. Now you will move X here, then you'll move A here. When you are doing all these things, why you are doing it? To make a place, right? Make a place to make a room to place Y. And from where you will fetch the Y, you'll fetch Y from main memory, right? So you'll go to main memory, and this is your main memory, and from main memory you'll fetch Y, and this will take some time. So during this time you can do all this swapping, right? So you have some time, you have enough time, and during this time you can do this swapping, that X will move to in place of N, then A will move in place of X, and then I'll make this position empty, and this empty position will ultimately store the block of Y. So yes, all these things you can perform in background. That is one answer, and that answer was very valid on 2010. That answer was very valid on 2010, that if you go with this, then this is a good design. But in today, if we go with 2020 and if we go with TCMP design, then this may not be a correct option, because now we'll go with multi-bank, right? We'll go with TCMP, and in this TCMP it may be possible that when you one core requested for a block and you are now in main memory, okay, and waiting for this block Y, at that time there will be another core here which is also requesting for another block called Z or something, right? So in this case, when the second core is requesting for Z, maybe your cache is now busy with doing all the swapping to adjust Y, right? So when it is doing swapping, it means that you are reading something from the cache, you are storing it somewhere else. So your cache block is busy. If your cache block is busy, it cannot serve another block, right? Another request. So when there are multiple requests coming in your cache, then maybe the swapping that is happening in the cache, that latency will fall into critical path. And otherwise, if it is a single bank and the requests are coming sequentially, then maybe this is not falling in the critical path. So they're both way possible. So I think if you read the paper in 2010, they assume a single bank design, and they said that this is not falling in the critical path. But in 2020, obviously this is falling in critical path. And but why I'm explaining it, maybe when you do your term paper, if you know this paper, maybe you will try to find out a solution where it is not falling in the critical path, and we can still use the concept of Zcash or skew associative cache. Okay, so Zcash, skew associative cache are important. You read it properly, and when you are reading, you don't think about advantage and disadvantage, because we are gradually developing the knowledge, and you cannot just start with 2022 papers, right? We should start gradual knowledge. We should understand all the previous works also. That's why I have started from 2005. And when you start your term paper, it will be your responsibility also to read the recent papers, because I'm giving you just a foundation. So now from that, this foundation, you can download any replacement policy paper or any partitioning paper, and you will understand it. But if I don't give you foundation, it will not be possible for you. That's why I'm explaining the basic papers, the old papers. And just after midsem, when I'll share the term paper topics, I'll give you some recent paper of after 2015, and it will be your responsibility to read those papers and understand it. Obviously, both me and Prathamesh will be here to means explain you, or if you don't understand any concept. Okay, so I think it is already 9:55, so I'm stopping my lecture here. So all the three papers that I have explained today, out of these three papers, VUA and Zcash are important for your exam. Okay, if you have any doubt, you can ask now.
Good morning, sir.
Hello.
Sir, am I audible?
Yes.
Sir, in the first paper, what if, sir, means in the first paper,
Huh.
the victim block is being selected from all the sets which is least recently used, na?
Victim block. There are two ways of victim block selection here. See, if this tag is full, okay, if this tag is full, and if you want to store some new data, new tag in this, then there will be a victim from here first of all, right? And if there is a victim from here, if you delete a victim from here, then corresponding data will also, suppose the corresponding data is here in this position, so you will also delete the corresponding data. In that case, you are making a space in tag as well as you are making a space in data, so no problem, you can directly place the block. You are understanding it?
Yes, sir.
Yeah, but the another problem here is, suppose in this tag, this is the situation where there are two more space available, but the data is full. ये हो ही सकता है, right? Because the data is only half of the total tag size, because some may assume that other sets are using it, and now data is full, and you are requesting for a new block which is mapping to this tag set, and this tag set has two more entries here. So अभी क्या करना है? One way is, even the tag set is not full, remove one from this tag. Maybe you can remove this, and is in this position you place the new one. If you remove this tag, then उसके साथ साथ एक data भी remove हो जाएगा. But what this paper is saying that no, don't do this. Instead of this, अगर यहाँ पे आपके टैग में दो पोजीशन खाली है ऑलरेडी, so first will go to data, and data से in data there is a global replacement policy. वहां से ग्लोबली एक विक्टिम ब्लॉक को चूज करेंगे उसको रिमूव करने के लिए. सपोज वो ग्लोबली जो रिप्लेसमेंट पॉलिसी वो बोल रहे हैं कि रिमूव दिस डाटा. अगर आप इस डाटा को रिमूव करोगे, मे बी दिस डाटा इज एसोसिएटेड विद सम अदर टैग, सो यहाँ पे एक बैकवर्ड पॉइंटर रहेगा, दैट सपोज दिस बैकवर्ड पॉइंटर इज सेइंग दैट दिस डाटा इज एसोसिएटेड विद दिस टैग, सो आपका ये टैग भी डिलीट विद दिस डाटा, एंड नाउ अल्टीमेटली दिस will be, this data position will be free for new block. इस जगह पे अभी now you will place this data and new tag will be here. So there are two ways. This is the second way that I am saying, if data is full, they are first selecting using a global replacement policy, selecting a data, and then removing that data and corresponding tag, and in the new the data that currently backend, उसके जगह पे नया block आ रहा है. Is it clear now?
Yes, sir. Yes.
Okay, you read the paper, I will understand it more.
Okay.
Obviously there is a disadvantage, there are both are disadvantages here, but I am not saying a disadvantage here, because assume that if we are in 2006 and the paper is published in 2005, so उस time पे हमें ये सब disadvantage नजर में नहीं आता, right? So I am explaining in this that angle now. So one disadvantage is global replacement policy is always expensive today, because if you assume at that time maybe they have consider 1 MB or 2 MB of cash, today last level cash are 16 MB and 32 MB cash are also common. आप इसके ऊपर आप अगर जाओगे ग्लोबल रिप्लेसमेंट पॉलिसी मेंटेन करेंगे तो it's an huge overhead. So I am ignoring these overheads now. We'll discuss all this when we'll start doing term paper.
Okay, sir.
Okay, so it is already 10. I'm stopping it here. So if you have
Sir,
any
but
other doubt, you can give
if,
me.
sir, but if someone is reading this paper, sir,
Ah.
and we don't have much experience about that, this, this amount, this global replacement policy is expensive uh, for around means this much of cash, this amount of cash. How will we know about it?
I
That's
can
little.
you please repeat your question? I couldn't understand what you were saying.
So I'm saying that you said that a lot of drawbacks are there,
Huh.
but the person like we are reading it first time, so most probably we won't be getting this. Now that uh, the, for this cash, this amount of cash, the global replacement policy will be mm,
Ye- Okay, so you are saying how
costly.
you'll understand that this paper has drawbacks
This
also, right?
yes, yes,
Only you will only understand it with experience. That's why at the beginning when you start research, always follow what your advisor says or what your senior says. Suppose in that case I am your advisor, and if I say Prathamesh is an experienced person, that's why I have took him he is an TA, right? So you always take advice from some expert at the beginning, and once you spend 6 months, you will have the ability after 6 months. If you spend 6 months on computer architecture or memory, after 6 7 months you will also have an ability, you will easily understand that okay, this paper has this limitations.
okay, sir.
Okay, so initial step is you read a paper, you discuss with an expert and try to find, and then listen what they are saying. This is the only way, but after 6 7 months you will get an idea, and at that time it will be easy for you to find out the pros and cons of each paper by yourself.
Okay, sir.
Okay, okay, thank you. So I'm stopping the recording here. You can leave if you have any other class now.